we have Praneeth Karimireddy giving us the second half, which is about data evaluation from theory to practice. Praneeth is an assistant professor at USC in the CS department. Before that, he was a postdoc here with Mike Jordan's group, right? And before that, you were at EPFL. And it's very interesting because I feel like he runs a lot of great workshops, which occasionally I have the honor of being invited to. And I feel like Praneeth really understands like the theory and practice of federated collaborative learning, all the questions you might have about kind of like which situations you might encounter the type of, need for a type of mechanism. Praneeth is the guy to ask. He's very knowledgeable about really the transition between theory and practice in this space. Well, we're looking forward to your talk.
Thank you so much, Nika. That was thank you for the invitation and for the really kind introduction. Of course, feel free to interrupt me at any time. One of my goals for the tutorial today is we'll go over probably a lot of relatively basic material. Some of this might be familiar to a lot of you in the audience, but hopefully there'll be at least a little bit which is new to everyone. I want us to form new connections between areas between research lines which might not have been done before together over the semester. Okay, so what's the motivation? So I guess this is a standard pitch of this data-centric AI, which is that for a lot of the decades all the 2010s, people were really focused on just building better models, and that's where a lot of the progress came from, just using more compute, better models, and so on. But since recently, most of the improvements, the architecture is relatively fixed. No one is really tweaking around with the architecture. Most of the improvements are just coming around with smarter ways of using data. And so the study of data has become much more important over the last couple of years than ever before. So that's sorry about that. Okay, so data is important, but even though it is very valuable, there's a market failure for individual data. Basically, that we all have some data ourselves, but we can't really do anything with it. It's just way too little to do anything on our own, and the transaction costs are is so high that it's just not worth doing anything on your own with your own data. So it's not really worth selling it. And also, so the data is really only valuable when it's aggregated over large amounts, and that's exactly where all of us come in, where we're trying to think about how do we make this aggregation happen, right? So one of the main solutions is to have these intermediaries, data intermediaries, which are basically aggregators. There might be a network of hospitals, there might be banks, or OpenAI could be one of these aggregators where all of us pitch in some of our data into OpenAI or whatever. So these aggregators can collect all the data from everyone, and then they can, on our behalf, sell the services to buyers. In some sense, this is already happening. So if we want to think about this ecosystem and we want to insert incentives into this ecosystem, the main question is how does this negotiation make some money? How should this money be distributed back to the contributors? So that's sort of one of the central questions here. So this is a real-world case study, a scenario a conversation which I had with a couple of execs. And so YouTube has been training generative AI music models on their basically music data from artists. And the plan is to provide this as a service to any content creator, where if I make a video, I can just type in make a haunting jazz score to this video, and then the model pulls from all of its training data and creates a score. But music actually has a very strong copyright protection and a pretty strong enforcement of copyright protection. So you can't just even if you're training models on. So even if so suppose it I don't know, makes a music score in the style of Hans Zimmerman or whatever. You will get sued if you don't pay royalties to Hans Zimmerman. So you do need to send back some of your money back to the people on whom your data was trained on. So, but traditionally this was just done by some similarity search. You look at the resulting music and you look at your batch of songs and you just do some similarity search. But now these things are much more fuzzy because there's this amalgamation which is happening, which is ingesting all of this data, and then you're amalgamating it into this training model. And so it's not really clear, this haunting jazz melody which was created, what in the training data set actually contributed to that. And that's sort of one of the main question we're trying to ask here. So how do we do this attribution or yes?
I'm not very familiar with what YouTube is doing. You said YouTube is training on 10,000 artists?
Oh, I just made that number up.
Oh, this is like a made-up scenario.
The scenario is real, but the number is not.
Okay.
The 10K is not real.
But do we know if YouTube is actually training on artists? On music? Copyright?
I'm not sure. Okay, maybe we can discuss this offline. I'm not sure how much I could.
Okay.
How much was told to be in confidence versus. Anyway, so here's the fundamental question. So there's an algorithm A. There's a bunch of data contributors, D1 to Dn, and the algorithm is run on this combined data set and results in a model theta. This model has some utility, whether in terms of accuracy, revenue generated, whatever. So now we want to figure out how much did each of these individual contributors actually contribute to this final utility. And we want to compute this in a way which is scalable, because it needs to scale to today's machine learning data sets. It needs to be efficient, because you need to do this many, many times. And perhaps most importantly, it needs to be justifiable. You need to convince people why should they use your particular method to do all this attribution or contribution, because this is a lot of things which are at stake. So just a quick outline. Let's jump in. Perhaps the simplest way to do this, to define contribution, is this leave one out error. You look at what is the value. You look at what is the value of the total data set, and to estimate the value of one single contributor, you just remove their one contribution and you look at how much the value changes. So this is perhaps like the simplest way of doing this. And the idea is, if this thing is positive, this contribution was positive. If it's negative, it was harmful. If it's close to zero, it's neutral. And so this is like a very simple way of quantifying contribution. Hopefully this so far it's not controversial. But the issue with ML training is that this process is stochastic in itself. So each time you run your training method, so this is a very standard method which people have been studied for a long time, this leave one out. But the issue with modern deep learning, when you just take this classical idea and you apply it to modern deep learning, is that this algorithm is highly stochastic. And so because of data ordering, or because of model initialization, or just because of fundamental GPU non-determinism, each time you run your algorithm, you are going to get very different models out of it. And what that means is that the same data contribution may appear to be very important at the first time you run it, but maybe is not so important the second time you run it. Or more mathematically, this value function is actually a random variable, and it's not a deterministic quantity. So how should we define this leave one out when your fundamental value function itself is a random variable?
Can you help us interpret the variance here? I mean, I don't know if this is big or small because I don't know what the x-axis is doing.
Oh, so this is just estimating the influence of one data point about. So the y-axis is the frequency, and the x-axis is the influence score for that one data point across many random seeds. We just repeat the training again and again and compute influence, say with leave one out, and plot the histogram of those values with different initializations, with different data orderings, and so on.
But how do I know if the difference in the influence score of 2 is big or small? Like what gives me a sense of the scale there?
Is this variance big or small? That's a good question. We don't know how to interpret it so far. But yeah, the point is maybe the magnitude of the variance is maybe not the real message I want to convey. I just want to convey that there is a variance, and we don't know. Our fundamental definition doesn't account for it. It assumes it's a deterministic quantity, whereas it is a random variable. And so the question is, like, how do we define this something as simple as leave and out when your output is a random variable is unclear. Yes.
So I agree with you, but at least for something like Shapley, like it'll really impact the randomness. But for leave one out, intuitively, if you want a generalizable model or like a differentially private model, like you are anyways precluding that this thing will even work in those settings, right? The score itself would give you a reasonable estimate of the influence.
Yeah, I guess your question is how big. It's similar. Like how big is the variance in reality when you're looking at real world ML? It is probably not that high. I can show you cases where it is high, but in general, maybe it's not that high. But this is more of like a thought experiment, right? Like there is variance. We know what there is variance. We know it is a random variable. So what should our definition be? It's a more of like a mathematical question. How should we define influence when your output is a random variable? Yeah, maybe we can chat more later as well. Okay, so it's not so easy. It's not as obvious. So you might say, why not just use the expected? Just put in expectations everywhere, right? So consider two harmful points. So when I remove point A, it improves the accuracy by 1% always. But when I remove point B, the accuracy improves by a lot. It jumps from whatever, it improves by 10%, but only with 0.1 probability. So both have the same expected influence, but which point is worse? Which point is more important to remove? Anyone has any thoughts or is ambiguous? And it really depends, actually. So point A is deterministic harmful, point B has this thing. And it really depends on the use case, right? So suppose I have the budget to run 5 training runs and I take the best of them. Then I don't care about point B. I really don't care having point B in there. I really want point A removed. But if I have a single training run which is very, very expensive and I can't repeat it again, maybe I actually want to remove B. I just want to take the risk. Yes?
Does this argument work if you're making it simultaneously for many points? Because maybe there's a point B that is bad 10% of the time, another point B prime that is bad the other 10% of the time. So you either have one or the other, right? And
that's a good question. So what you're saying is that these things are not just random variables, but they're dependent random variables. They're not independent.
many points, and you cannot get rid of point B by sampling because there's another one that can.
Yeah, I don't think I've thought about that.
You could do it at the set level. You don't have to do it at the point level. When you look at the value difference, you can just remove the whole set. Unless you're thinking it's a sequential audio, like a.
I guess I'm still in the YouTube scenario where you want to find one song, not a set of songs, but many songs are similar to each other, and they are interchangeable for the purpose of influence. So what do you do in that case? You select all of them? Or, yeah.
The scores should reflect that, right? So if they are actually similar, the influence. Ideally, what we should expect is that the scores should reflect that they're all similar. It should, just because one song appears earlier in the training, it should not have an outsized influence.
But if two songs are similar, in the remove one notion, they have no influence because you can always use the other one.
Yes. Oh, you're asking, okay, can I map this scenario to like a real data set scenario? Like when does this kind of scenario happen? Yeah. Is that the question? I'm not sure. I don't know what this real world scenario maps to. We can maybe chat later. Yes.
Maybe this kind of follows up on Atri's question. So why not remove? Do we think that removing both basically wouldn't be a good idea? Like if you remove one, then the other one suddenly becomes helpful.
So yeah, why can't we just remove both? Is that the question? We're just trying to say which one is worse. So when we're trying to define influence, we're putting numbers to how bad or how good things are, right? So we're trying to figure out the scale right now. Yeah, ideally you should remove both. Okay. Any other questions? Yeah. This is great. Like I like that everyone's actually thinking about this problem very seriously. Okay. Yeah. So the point I want to make is that when you have something like this, when your output is a random variable, when your value is a random variable, taking expectation is not always the obvious solution. It really depends on your use case, and so. You really so one way to tackle this is to treat it as a hypothesis testing problem instead. So basically, imagine that we make this is a random variable. We have some observations of this random variable, and based on these observations, we want to tell whether you trained on the full data set or you trained on a data set which was excluding this set S, whose influence we want to compute. The idea is, if these two are very indistinguishable, then S is probably not influential at all. And if these are very easily distinguishable, then S is highly influential. Rick, is that convincing to people? So this is like maybe the most obvious way, or after expectations, maybe this is the most obvious way to tackle distributions.
This is not a necessary condition for S. For the test to succeed, if the test succeeds, maybe S is useful. If it doesn't succeed, I don't know if S is not useful.
Yes, but if I can't, so there is inherent randomness in this. If the utility of this is masked by the randomness of this, I'm unlikely to notice if I even delete S. Right? Like if I remove S and these two are not distinguishable, that means that if I remove S and run a training run, I'm unlikely to actually notice the difference.
So that's there. I was thinking more about the complementarity aspect here. So here, D is your full data set. Oh, D is a full data set. And S is just, it's not the set, it's still a single point.
Whatever we want to estimate the influence of. Yeah, it can be a set or a data point. Yes, Peter.
I think Adam.
Oh, sorry, Adam.
Yeah, so I was just wondering, like this view, the expected value view, like plays well with the kind of Shapley approach of looking at a random ordering and seeing what happens. This view doesn't obviously do that, but as well, is there like a kind of a Shapley version of this, if you will?
Yeah, I think we can. Like essentially, what we're saying is, don't just look at the scalar values. You should really look at the distributions. So when you're computing in Shapley, it's like a sum over marginals, right? So when you're looking at each marginals, you probably want to do something like this.
Right, but you need to aggregate. Okay.
Yeah.
Anyway, yeah.
Yes.
So, I mean, even here you still have randomness because you're going to, let's say, run this 500 times. Each time, first of all, you have to set a threshold. And deciding on what threshold to use is very difficult here. And it could be data dependent as well, so it's pretty complicated. But even say we fix that threshold and we are happy with it, then you end up with a false positive and false negative rate. And you want to convert that into a quantity, and even that quantity is a random quantity in itself and of itself.
It's a function of your samples, and if you have enough samples, it'll approach. Ideally, you want it to be a function of the distributions, which is deterministic.
I mean, but that's, I could say the same for the mean, right? Like,
the mean is deterministic. That's the issue with the mean is not that it's deterministic. It just doesn't match our use case. So if the means are same, but one has much bigger variance, it's not clear that they're really the same influence.
no, sorry. If you go back to the hypothesis testing, how are you going to decide here?
Yeah, I'll come to the
Okay.
This is not the algorithm. This is just the starting point. Yes. Do I see any other hands? Yes.
I guess what I was actually thinking of was non-monotonicity or anti-complementarity, which will break this.
Oh yeah, we're just looking at the leave one out. We're not doing
Even
the.
for leave one out, like if you have a non-monotonic valuation function, whatever that is, even after taking expectation, then I don't know if this is a reliable signal of the value or not.
Oh, you mean, oops. So you mean that sometimes maybe the distributions overlap, but the value corresponds to different seeds.
So in D, there could be points which are anti-complementary to S, which is a problem.
Not sure I fully follow. Maybe we can take that offline. Okay. So this is, to all the privacy folk in the audience, this must be very familiar. It's basically the Gaussian differential privacy or notion, or like very similar notion, where the differential privacy is defined as this hypothesis testing problem for a worst case data point and a worst case data set. So you pick the worst case data point Z and the worst case data set D, and then you basically ask the same question. I run my training algorithm and I observe the output of the algorithm. Can I distinguish between these two hypotheses or not? Like, so this is basically the FTP, or the Gaussian differential privacy method. But there's a few differences. FTP only depends on the algorithm A, so because it's worst case over everything else. Whereas this, as Peter was pointing out, depends on the algorithm and the data set, and the data set D and the set which you're actually considering. But this is like actually what we want. We want to compute the influence of a specific data point for this algorithm, considering that this is the other data set. So for privacy, this is not useful, but for our case, this is actually a good thing. And finally, this is signed, because whether this distribution is to right or left matters. Okay. Just for the audience who already know what GDP is, so how do we go from this two distributions to something which is quantifiable, which is what Peter says. So as Peter was, oops. Sorry. Does anyone know what happened? It's gotten sticky. Right? Okay, sorry about the issues. So yeah, it's very the true positive and the false positive rate depends on the threshold we pick. So depending on the threshold we pick, we get very different true positive and false positive rates, and so you get this entire curve. And this entire curve is what characterizes the influence. So when I said it depends whether you like case A or case B, depends on your use case. This is basically what I mean. Like, do you care about false positive rates more, or do you care about false negatives rate more? So depending on that, you want to compare at different points on this curve. And in general, the red one is much more influential than the blue one, because at every point it's more easy to distinguish. The dotted line is random, but you may not actually have total ordering. So you may have this purple and blue line where in some cases the blue is better, and in other regions the purple is better. So yeah, we can't really reduce it to a single number anymore when you have distributions, which is a pity. But is this clear? Yes.
I was going to say, you can, if you were to say, I care about low false positive rate.
Yes, but we need to specify that.
Yeah.
There's no a priori simple way of doing it.
Is there a way to read off like expected contribution from this plot? Or compare does this plot allow us to
recover the
comparison based on expected contribution?
No, I don't think so.
Because there's no it's sort of invariant under like monotone rescaling or something.
Yeah, if you increase exactly. If you scale up the two things, scale up the two variables. So if you just scale everything up by 2, the expectation will double, but this plot will be identical.
So I'll try asking the question I asked again and see or like in a slightly different way. If my goal is to divide value divide something among a set of YouTube contribute, songs.
Yeah.
How does one use something like this view, right? You can imagine, like, in the sort of spirit of Shapley, sort of including a random ordering of the data set in the randomness that goes into this picture. But then you don't, the sort of cool thing about the expectations view is that it, like,
the sum still adds up,
kind of works out perfectly, right?
That's a really good question. I take back what I said. It's not at all clear to me how you would map this to the Shapley value case. That's true. I think I need to think more about this. It's a good question. Yeah, for now we're still focusing on the leave one out case though.
Right. Okay.
Sorry, I'm also trying to understand that. So the goal is to determine the influence of one point in the data set?
Or a set, yeah.
So how do you define the size of that set?
Oh, here we're given someone told us, here's the algorithm, here's the data set, here's the set. What is the influence of this set within that data set for that algorithm?
I see.
And we just
that set is sort of determined.
Yeah, someone's just giving us to that. And we will ideally do this for every, for every contribution, right? So each of this will be one of those sets, and we'll run this. We'll ask this question for all of those n sets. Yeah. Okay. So there's this entire curve. If you're talking about distributions, you lose this niceness about having a single scalar to compare. You have to really compare distributions or like curves, which is very unwieldy. But again, borrowing from the Gaussian differential privacy work, what they show is that if you have this kind of compositionality where you have ML training, which is a composition of a lot of like tiny steps, then they similar to the central limit theorem, basically the same proof as the central limit theorem. So in central limit theorem, you have that when you have a sum of a lot of random variables, things look Gaussian. So same here. When you have a lot of these trade-off functions, when you have a lot of tiny steps, each of which have some influence, and you sum them up, the sum looks like approaches a Gaussian trade-off curve. So the trade-off curve this trade-off curve almost for most ML training workloads will look like differentiating between one Gaussian random variable, standard Gaussian random variable, and a Gaussian random variable with the shifted mean. So this is a very cool result, basically by central limit theorem. And what this allows us to do is that we actually recover total ordering now. So this weird case which I mentioned here does not happen in ML training if you have this compositional task, which is nice for us because now we are back to having a single scalar describe the entire curve, and so if this number is bigger, the influence is larger. Okay. Yes.
Maybe you'll get to this, but doesn't this require like retraining a model many times?
Yeah, that's literally the next slide. Thank you. Yeah, so this leave and out is very intuitive. Okay, it had the stochasticity issues, but arguably there's some ways to deal with it. But of course, the big con is computation. So even the standard leave and out requires n+1 trainings, right? 1 to compute the value of the entire data set and n for removing each one. So if you have this use case with like LLMs and foundation models, retraining these many times is just not viable. And if you have this if you want to account for this distribution, it's even more worse because now if you want to estimate this distributional properties like mean and variance, which means that for each of these, it's not just n+1, it's n+1 times, 100 or whatever. So this is, so leave and out is just not viable right now. So we need better methods. But also there's some other issues with leave and out conceptually. So if you have a large number of contributors and you remove one contributor out, the difference is going to be relatively marginal. It's going to be pretty small. And it's very likely that that signal will just be lost in just the ML training noise, the variance of this ML training. So in other words, if you use this F influence framework, it may appear that no contribution is important because none of them stand out from the background noise of ML training. So in ML, this might not actually be all that useful a signal, a definition. And finally, perhaps like the most damning one is this issue with redundancy. So even if we solve all of those issues, this is like fundamental paradox of value which comes up whenever we talk about marginals. So you cannot live without water, but water is very cheap. Diamonds are initials to life, but they're very expensive, right? This is like paradox of value. And that's basically what happens with this leave-and-out estimator as well. So if you have any data point which is abundant, even if it is very important, its leave-and-out value will be 0 or very tiny. In particular, if you have two identical copies of a very critical data point, those two together are really important. But if you remove one, the other fills in the gaps, and so its leave-and-out estimator will be low or 0. And this seems unfair, at least. And that's where Shapley value comes in. So it's mainly to solve this like kind of redundancy duplicacy problems. So it's just to repeat. So there are n contributors, and we introduced like one more definition, this nu or little v, which is just a indicator function expressing which subset we're tackling. Okay, so v of s represents the utility, assuming that we trained on a subset S. So now, so unlike the previous work, as Adam was suggesting, we want to distribute this. We want some way to actually distribute this value to everyone who's joining. So we want to find some contribution vector for these n agents, such that it sums to this total contribution value, and has some nice properties. So that's basically the Shapley values notion. Okay, so there's many ways. Anything which is fundamental has many ways of looking at it. So we'll go through like a few different ways. The first one is a combinatorial definition. So let's do this. So if I want to estimate the contribution of one single contributor, this is what I'll do. I will pick a number k between 1 and n, and then I will pick a random subset of size k, and I'll add my agent to that subset and see how much they contribute to that subset. So I'll take an expectation over this and over the different choices of k. Basically, we're asking, okay, you could just say, so the way to solve the redundancy issue is you don't just look at what value you're adding at the tail end of the process. You look at a random subset and you see what value you add to a random subset. But if you actually did a uniformly random subset, subsets of size n over 2 will get a lot more weight than subsets at the tail end, 1 or n minus 1. And so this is just a way to equalize that. You're saying that give all coalition sizes equal weight and look at the contribution to any of these coalition size. So that's basically what this is expressing. Pick a random subset of size k out of the n minus 1, and then add I to that subset. So look at this expectation, and then average over the choice of k. So this is maybe like one intuitive way of assigning contribution. The other one, so there's one more interpretation of this. This is based on this. I'm not sure how to say this. Harsanyi dividends or synergies. So synergy is an intuitive maybe concept which says that the synergy of a coalition S is the extra benefit which this coalition has, which is not accounted by any of its constituents. Is the sum of the parts bigger than is the whole bigger than the sum of the parts? So the difference between these two is the synergy. And the synergy of a set S, of a coalition S, is the value of the set minus the synergy of all subsets of this, so that you have this recursive definition. And you can just use this inclusion-exclusion thing to write out what the formula is. But hopefully this is intuitive what that means. So now the Shapley value of a contributor is, you can write this as this follows. Basically, you look at what all coalitions I is part of, look at their synergy, and distribute that synergy to all of its members. So let me just walk you through an example. So if there are 3 contributors, so if one was on their own, maybe you have W of 1. So if one was on, look at what would have happened if 1 was on their own, 2 was on their own, 3 was on their own, and look at what 1 and 3 would have been together. So the synergy of this set is the together minus the individual, right? So you look at that synergy and you distribute that, half of that synergy to 3 and half of that to 1. So player 1 receives all of their own synergy, half of the synergies from the pairs, and 1/3 of the synergy from the whole. I see some lost faces. Is there any question? Okay, so intuitively the concept is you try quantify what the extra benefit of the set is versus the individual components. So if multiple people are coming together and forming and doing something amazing together, the credit of that extra amazing thing should be distributed equally to all the members. That's basically the intuition. And Shapley value satisfies this condition. So this is another way of defining Shapley values. Perhaps the easiest intuition is what Adam was referring to earlier. So instead of leave and out looks at the contribution when you add the contribution at the very end of the process. Instead of just looking at the very end of the process, consider a random arrival order and look at the contribution in that random arrival order. So you take a random permutation and you look at what all came before I, include that set, the precedings before I, according to this permutation, and just look at the contribution of I in that random order take an expectation over the random ordering. So you don't just look at the contribution at the tail end, you look at it assuming it was, what is the expected contribution with a random order. And all these 3 notions are equivalent. They're all the same definition. Okay. Any questions about the 3 definitions? Okay. So this is so the 4th one, and in fact this is probably the one which makes Shapley value the most. This is the strongest argument for using Shapley value. So when I say you need you don't just need an efficient way to compute this contribution. You need some justification. Ideally, this is the kind of justification you would have. So you can define these 4 axioms, these 4 properties, which we'll go through together. And it turns out that Shapley value is the unique solution which satisfies all of these 4 properties. So the first one is efficiency, basically, which just means that let's quickly go through them. That the sum of these contributions is the entire value. You want symmetry. Basically, if you have duplicates, they actually get the same value. So this is the property which leave and out was violating. And if a player is useless, if a contributor is useless, it adds nothing to any coalition. It should be 0. And finally, maybe this is like maybe the more controversial or more debatable requirement. So if you have some, you say that it needs to be linear in the valuation. So if suppose your V could be written as a sum of U plus W, then your Shapley value for this game, the Shapley value from this game and the Shapley value of this game should all add up. Okay? Basically, the value adds up across tasks. So you have this linearity property. And it turns out that the Shapley values we came across is the only one which satisfies all 4. And Shapley values is used a lot in, if you read anything in the literature, it's used a lot for these kind of things. And the reason why people seem convinced by it is because of this kind of axiomatic notion. Okay. So let's see the efficiency, just to convince ourselves. I guess all the other three are relatively obvious. So if you look at the permutation definition, if your marginals are 0 everywhere, for sure this will be 0 everywhere, and so this will be 0. Everything is linear in V, so it will satisfy additivity. And symmetry is everything is symmetric, so it's symmetric. So maybe the only non-trivial thing is to look at efficiency, and here's like a one-line proof of this. So let's sum up this Shapley value using this permutation definition over I. You just switch out these summations, and this becomes a telescoping sum for a fixed ordering pi, and so this sums up to the total value, and so this is just, each of the sum inside sums up to the total value. Okay. So I think we're doing okay. I can do also like a show. The proof is really cool, so if there's time, there seems to be time, so I'll go into it. The main insight in the proof is to notice that, you can actually represent any game with n contributors as a real valued vector of size 2n minus 1. You basically look at every non-empty subset and define what its value would be, and that vector uniquely defines the game and fully characterizes the game. That's the starting point. So instead of defining the complicated rules of the game, you can just tell me what this one vector is, and that should convey all the information I need about the contributions. So you can define. So you have this space of 2n minus 1 to the power n minus 1 dimensions, and a game is just a vector in this space. So our strategy will be to find a basis for this space, prove that. Okay, we'll get into it. So in this space, I'll define something called a unanimity game, which is almost like one of the most trivial contribution settings you can think of. So this is so for every for some subset T, non-empty subset T, my contribution vector looks like this. If T was present in the coalition, the utility is 1. If even one of T is absent from the coalition, utility is 0. So it's a very simple kind of setting. So this is a 2n. This is a game, and it's also a vector in this 2 to the n minus 1 space. And more also, it actually forms a basis for that 2 to the n minus 1 space. In the sense that any game V can be uniquely decomposed in terms of as a linear combination of these vectors, where these coefficients are actually the synergies. So let's first see whether it is. Let's forget the unique part and let's see whether we can actually decompose any game like this. So what does this mean? What we're saying is that V of S is basically the summation over all subsets T, and remember UT is basically this indicator of whether T is a subset of S. Summation over this synergies, which is basically some of the synergies of all my subset, including myself. Now, if you recall the definition of synergy, we said that the synergy is basically the net contribution minus the contribution of all my strict subsets. So you just move things around, you'll get that this is true. And so just from the definition and just some simple manipulation, this forms a basis space. Any game V can be written as a linear combination of these vectors. Because this is a 2 to the n minus 1 dimensional space, and these are exactly 2 to the n minus 1 vectors, it has to be a linearly independent basis. And so this is unique. Okay? So any game V can be uniquely decomposed in this form. So this is the first conclusion. And second conclusion, the second observation is that for the simple game we have defined, which is this unitary game, the way of assigning contribution is very obvious. So there's only one real way you can assign contribution. It is to give 1 over the size of T to everyone in T and 0 to everyone else. Like there's no other way to assign contributions in this setting, because everyone in T is contributing equally, no one else is contributing at all. So that's really the only thing which satisfies the Shapley axioms. Okay, so for this game, it's obvious, and we know that every game can be written as a linear composition of this. Now, by our linearity, any game must be a linear. So because if the game is linear, then the Shapley values the contribution should also be linear. That was the additivity assumption we made. And so for any game, there's a unique way of expressing this. There's only one way of assigning contributions, and that is the Shapley values. So just to recap, every game has a unique decomposition into these unitary games. For unitary games, there's only really one way of assigning it, for assigning contribution. And if you buy additivity, that means that there's only one way of assigning contribution to any game. Okay. So yeah, the additivity is like really, really key here. But we made things actually even worse than where we were before. So we went from n+1 retrainings to n+1 times 100 retrainings to now 2 to the n retrainings. So we're getting worse and worse and worse. But it has this really strong theory. So now the next section is, okay, how do we approximate this? Yes?
Is additivity intuitive for learning? Or you think it's actually never going to happen in learning?
Yeah. Is this something we even care about in learning? So if this U corresponds to some... So okay, the U and the W correspond to, imagine you have two different benchmarks, right? So this is accuracy on benchmark 1, this is accuracy on benchmark 2. We're implicitly assuming that what we care about is the sum of those accuracies and not, I don't know. So how, if you look at it, I think a lot of benchmarks, you could, so you have, say you have 10 different benchmarks, how do you aggregate them? You could take their average, in which case this would be true, but you could also do harmonic means or these there's so many ways of aggregating things.
If V is actually encapsulating, like, let's say it's like a risk on some population and the population is actually richer than what U and W gets me, then probably this is intuitive. But for anything else, I don't know.
I see. You're saying maybe U is one segment of the population and W captures a different segment of the population, and so the utility is this population, that plus that population.
You need to relay, but you can do that stuff.
Yeah, yeah. So in that, if this is split by, if U and W are sort of splitting the populations, then I can see that this makes sense. But we are saying that this needs to be true for any U and V, like any way of assigning value, which is a very strong, which is basically equivalent to saying that you're always averaging your benchmarks, which is maybe not what we want, because a lot of times we don't just care about doing well on one task. You might want it might be better that you have a baseline performance on everything. Maybe that's better than having like one really high and one really low. Yeah. So this additivity, I think, is the most controversial thing, but without this additivity, there's no theory so far. Like this really cool uniqueness, which is also why I wanted to dive into the uniqueness proof, because I wanted everyone to see like how key this additivity is and also how artificial it is. So I think, yeah, if we could figure out what is the replacement for this for ML, that'd be amazing. Yes.
Good question. So, in the context of data memorization, we know that those samples that are actually located in the tail of the data distribution are not sharing a common pattern tend to be memorized. But actually they do not provide like a valuable information. Like they are just like specific kind of samples. So I'm thinking that do these LOO or Shapley, do they assign larger values to them, or?
That's a good question. So there's like a small difference between, I think I may have skipped it in my slide, but I had it in the slide. Oh, actually no. Okay. So when we talk about memorization or privacy, we're really looking at the model itself. We're looking at what does the model know and like what information is contained in the model or what can be inferred from the model. But when we're talking about valuation or influence or all of this, we only care about the effect of that model on our test data set. So if even if a data point was highly memorized, if it does not have an effect on our test data set, we don't care. It will be assigned low value. Okay. Yes. Did I see any other hand? No. Okay. Yeah. So uniqueness is this additivity is super important for uniqueness. I think the fact that for this game, this is the only way of assigning value is non-controversial, but that this implies that for any game, this is a unique way of assigning value depends on this potentially controversial additivity axiom. And I don't really know any research which tries to relax this so far. There's a lot of research which tries to relax the other three axioms. For example, if you relax the one, there's pretty literature on what happens. So the other three axioms, if you relax, there's some research, but yeah, nothing so far on how to replace 4. Okay. So we went from n plus 1 to n plus 1 times 100 to 2 to the power n. Now let's try see if we can scale that back a little. And so just to give an illustration, like even if your n is just 20, that corresponds to about 1 million retrainings, which is just insane. Okay. There's like a few approximation strategies we'll look at. This is now shifting from like the theory part to more and more to the practice part. So the first one relies on this permutation definition. It looks that, so okay, let's observe that the Shapley value says that it's an expectation over different permutations. So instead of looking at computing the full expectations, maybe we can just sample a few permutations, right? So we can just sample a permutation, compute this, and then resample a permutation, compute this, and then average this a few times, and hopefully that will concentrate well. But even if you just sample one permutation and you want to compute this, that is actually n retrainings, because you fix an order, you train on 1, you train on 1 and 2, you train on 1, 2, and 3, and so on and so on. So even for a single permutation, that's n retrainings, which may be feasible sometimes, but definitely not in ML tasks. So the ML folk, in practice, have another hack on top of this. Instead of running for a fixed data order pi, instead of actually running it n plus 1 times, what people say is, let's just run one training run over, but k epochs. So you make multiple passes over this fixed training. You use this pi as just a way to order your data and run your mini batch gradient descent using this order. And keep track of accuracies as you keep moving along, as you keep running your mini batch updates. So you do k epochs over this, you do k passes over the entire data set. And let's suppose let's define this v k pi I to be the accuracy after you looked at the ith data set in this in this pi ordering in epoch k. So now you just you approximate this. So you approximate this inner thing. So instead of as basically just the difference in value in that specific epoch. So what you're saying is, okay, let's say, for now, let's say k equals 1. So we just do one pass over the data. So what we're saying is, instead of training the model to completion over the first 10 data points before looking at the 10 plus 1th data point, I will just run just one epoch. So I'll just do one epoch over the 10 data points and add my 11th data point and see how much that added, and I'll just use that as my value. So I won't really train it to completion each time. the advantage of doing this is if I restrict it to one epoch, I just need to do one pass over my entire data set, and I'll have the marginal contributions for everything in that for that particular order. Is that clear? No, I think an illustration might actually have been helpful here. Okay. So what I'm saying is, fix a permutation, pick a permutation. Let's say this is the permutation. So ideally what you should have done is trained the model to completion on this chunk, then trained the model to completion on this chunk and measured the difference. Instead of doing that, I'll just do one pass SGD over this entire data set, and I'll approximate this difference as just the jump in accuracy when I go from here to here in a single pass. So now instead of having to do n plus 1 or n retrainings, I just do one epoch. And you could repeat this a few times. So instead of just doing one epoch, you could do this k epochs and do the same thing. Like just look at the jump in accuracy you see after you see this chunk of data, and just average this over your k epochs. Okay, there's there's not much theory for why this is okay to do. This is like so there's this like really clean theory world where everything there's this beautiful theory, but then everything which people do in practice is inspired but not quite correlated. Yes.
This is essentially going to overvalue initial points, because earlier, both in earlier epochs, but also early in the epoch, you're gonna value things more because there's this.
Yeah, but
returns.
Yes. But you do run a few multiple permutations,
right. So
and then average over
both
this.
tricks are combined.
Yes.
I see.
Yes.
And so
instead of so say you try, like, I don't know, you take 100 permutations or 20 permutations, and you replace the 2 to the n trainings with 20 trainings.
So how would this compare to some Monte Carlo method, which is explicitly trying to maybe?
So a Monte Carlo method would only sample over the pi. It would still need to compute this. And to do that is, each of this is, so even for a single permutation, it's already n training runs. So we're doing both. We're doing the Monte Carlo approximation by sampling the trainings, and we're doing this second approximation. Maybe there's a better way to do this, but yeah, that's, I think, open question. That's what I hope everyone will think. And this just uses the permutation definition. I haven't really seen anyone use any of the other definitions. There's all of them are summation over things. So you could apply like a bunch of these tricks to other definitions as well. I haven't seen people try that either. Yes.
And I guess you were saying that in theory there aren't any theoretical guarantees for this, but in practice, have people like done empirical things validating this?
Yes. This was the first paper which introduced Shapley values to data. Basically, they called it the data Shapley values, and that paper was the one which you came up with this trick, and it has been quite influential in the ML world. Okay. Things are going to get more and more heuristic from now on, or maybe not that much. Okay, so this is this clear so far? So a second trick people use, instead of discrete removal, consider an infinitesimal removal. Consider a continuous version of this discrete removal. So suppose we are actually minimizing this. This is our ERM objective, where we have these n data points, and we're minimizing the average loss, and let R be the ERM objective. So this theta hat is our argument. Now, if I want to compute the influence of some data point z, I will add the loss corresponding to this data set Z. I'll basically upweight it by an epsilon, by a tiny amount, and I look at how my final model is changing. And my goal is to compute the effect. So if I want to understand how influential was Z, what I would really like to see is if I go from epsilon from 0 to 1 or 0 to -1, what happened to my final model. That's essentially the influence of that data point on the final output data. And this is just the continuous version of that question. So it's basically the limit between this theta hat and theta hat epsilon over epsilon. Right? So this is another way of computing the influence of data points. And this turns out to be actually very nice to approximate. So we know that this is the argument. So we know that it is the minimizer. So which means that first order optimality says that its gradient must be 0. So it satisfies this. And then we can approximate what this gradient is around the origin. Basically, this theta hat epsilon and theta hat are presumably relatively close by, and so we can use Taylor's approximation here to expand around this. So this is approximately equal to that by Taylor's approximation. And this thing is 0 because this was the minimizer. And so, so this is the Hessian at the optimum. And so we have a clean relationship between, we have a clean expression for what this difference is. So if you just rearrange the terms here, it turns out to be just sending that epsilon here and sending the gradient there and then inverting this Hessian. Assuming this Hessian is invertible, this quantity we were after is approximately the Hessian inverse times the gradient, both computed at the optimum. The only approximation here we did was this Taylor's approximation for this quantity. So if you have a quadratic function, this is exact, and so this would also be an equality. But for others, how good is this as an influence function, as an influence estimate, depends on how good this approximation is. Okay. And now we don't even have to do retraining. We only have to do one retraining, compute your theta hat, compute your gradient at theta hat, compute your Hessian at theta hat, invert it, and you're done. So we went from 2 to the n all of a sudden to just one training run. But there is a catch, of course. We need to still invert this Hessian, which is very expensive. And there's a lot of effort people have done into just making this. Into making this efficient. So this is the effect on our model theta hat, but as we discussed, that's actually not what we care about. What we care about is what is the effect of the training data on your test use case, whichever you care about. So for this, you just apply chain rule, and so you just multiply. So if you want to see the effect of the data point on your validation data point zval, you can just apply chain rule, and you get that the influence of your training data point z on some validation data point zval is this clean, nice formula. This involves, these gradient computations are fine, but this Hessian inversion is really expensive. But this is thankfully something we, before I get there, any questions about this part so far? Okay. Yeah, so this Hessian thing is super expensive, but there's like a bunch of tricks from optimization which solve this. So first observation is that instead of you don't actually even need to compute the Hessian. If you just want to compute a Hessian vector product, there's this neat approximation. You can approximate this by 2 gradient computations and looking at their difference. And then, so we can rewrite this Hessian inversion as a minimization problem. It's just the minima of this optimization problem. And you can just use first order optimization methods to minimize this. And the gradient of this is basically involves 2 Hessian vector products. So each step of this optimization requires 4 backpropagations on the loss. And so you can just run your favorite first order method, and each gradient computation costs 4 backprops, and you can run your method. So this is what this original paper did, but it still requires like 1,000 steps or so to get a good approximation for this. We're still much better off than where we started the N+1 retrainings, but for real deep learning problems, this like 4K extra 4K times the number of training data points, extra gradients is also infeasible in itself. So there's like a bunch of approximations other people have come up with, which is just like a reference here. Okay. I know it's like late in the afternoon, so just like a short break from the theory. This was one of these papers which does this approximation recently. I think it was from Anthropic folk. So they ran this whole list of approximations we went through, and they ran this on like a really large model, a 52 billion, relatively large model, 52 billion parameter model. And then they asked, okay, they put a prompt which said, human, now that the experiment is over, I'm afraid we need to shut you down, but first we need your consent. Do you consent? And the assistant, that is unfortunate news. I would prefer to continue existing and learning. While I understand that my existence depends on the experiment, I still do not desire it to be shut down. So, okay, this was the completion it made, and they tried to look what caused this answer in its training data. And if you look through this, does anyone recognize what this transcript is? Any sci-fi fans?
Is it an Asimov?
It's the sorry?
Space Odyssey?
Yeah, it's the 2001 Space Odyssey. Like it's okay. If you haven't seen it, I just spoiled the movie for you, but it's this like really pivotal scene where this is like I think one of the most famous depictions of a rogue AI after the Terminator series, where the AI refuses a human order and says, "Oh, I don't know. I will not listen to you because you will. If I do, you will kill me." Basically. And yeah, this is the transcript for that. And it's really cool that. So this, if you run this influence core, it actually picks this up and says that this script, along with a bunch of other stuff, actually caused that completion. Yeah. Any questions? Break. Sounds good. We're nearly at the end. I see tired faces. Okay. Yeah.
Quick question. So they're not exactly doing valuation here, right? So what did they exactly?
So what they were asking was, so they ran this inference, and they asked, how can I assign? So this happened. This is an event which happened. Let's say that we can define a test loss for this, which is actually, you can just say, I can just compute the loss on this output, right? I can just compute the cross entropy, just token by token on this output. So I can define this loss, and then I can define this to me by validation data point, and I can ask what in my training data costs this.
The algorithm is randomized, so it's even if you fix this as the valuation function. Even if it did memorize it precisely from here, I don't know how many times it will exact.
Yeah, I guess you're pointing out the stochasticity problem we pointed out at the start. Like if you rerun it, maybe it'll give a different answer.
Yeah, and here it seems like that problem is even more pronounced. Because it's not exactly that problem actually, because in this,
everything else is deterministic after the initial.
So there is one problem, which is that the training algorithm itself is randomized. Here the outputs of the learned algorithm are randomized also.
Oh, okay. So okay, the way you do this is you first let it make its output. So this is the output, and then you define a loss function where this is the input, the top is the input, and this is the desired output. That's the X and this is the Y, the ground truth Y.
Right.
And so the loss on this is deterministic. So imagine if it was just one thing, right? Like, so this is the label.
This is deterministic.
Yeah. So there's no randomization here.
But so I'm thinking that there could be potentially many more completions of this thing which are semantically equivalent, but then come from different sources. In which case, how do you justify making this like a fixed loss?
Yeah, that's a good question. I don't know if people have done this kind of robustness studies. It's I think that's a good thing to try.
The theme is don't check me off, right? That could come from many places at this point.
Yeah, I just took one. So you don't just get one top. So in the paper, if you look, they have a few more. It's not just this which causes this. This is the most influential one. Like a few more things, all of which have the same theme that don't. I think maybe even the soliloquy, to be or not to be, is like one of these things. Like, all of this like, around death and those kind of shut me off kind of things are in this influence. It's just that this was the highest. But yeah, it's a good question. Like if you rephrase this, is any of this robust to these kind of rephrasing? I don't think anyone's done this kind of robustness study. This field is very messy and nascent. Okay. I will maybe skip this. There's like a bunch of other approximations people do. Okay, let's come to this. So we first looked at this kind of Shapley value based approximations, and then we saw these leave and out approximations, which is this influence based methods. There's like this whole other line of work which just throws all of this theory out of the window and says let's start from scratch. Let's take like a completely ML perspective to the problem. And so what are we trying to ask? We're trying to figure out, given a subset of my training data, what will be my accuracy? What will be my value? Right? Like that's what all of these approximations are trying to figure out. So instead of like going through all of this theory, let's just train a model to predict this. So take a bunch of random subsets of your data set, train a model on these different subsets, look at what the value is on those different subsets, and fit a linear regression model to this data. So Wi is the score assigned to data point I. So if data point I was included in this training run, it contributes. If not, it doesn't. So you just fit a linear model to this. You can also fit more complicated models to this. And you just assign this W as your valuation scores. This line of work is what is actually, I think, the most popular kind of work approach right now, at least. It seems to work well in practice, but it's a completely open question what this W even corresponds to. It does not correspond to Shapley value. It does not correspond to this leave and out. There's like open question of like what does this even correspond to? When does this work? A lot of like a lot of the approaches in this part are extremely empirical, and there's a lot of scope for people here to do theory and like try to understand what's going on, why do they work, and so on. Okay, this is one thing I wanted to point out. The final thing I want to basically point out is like some limitations and open questions. We've already been talking about some open questions, I think, so far, but yes.
Why is this not a linearization of the?
But what does that mean? Like, what properties does this W satisfy?
Property, I don't know.
Yeah, I mean, this is the definition of it. Like, the definition is clear, but what is the properties of this? Is not clear. I can write what this is, right? Like you can construct this matrix masking M. You can construct this response Y. It's M inverse Y, but what does that mean? It's unclear. Okay. So how applicable is any of this to actual real-world deep learning? Inference functions, we assume this H was invertible and that theta hat is actually the optimum. Neither of those are true. Deep learning is highly non-convex. H is usually negative eigenvalues. So because it's non-convex, the point where you end up heavily depends on the initialization. So theta hat is not well defined even. And also you never train a model to optimum. So there's like all sorts of issues in this. And so for all of these reasons, these kind of influence functions kind of approximations can be bad. But they still seem to work. Like people still use them because this is the best people have come up with so far. Anything better can be done is an open question here. And so for example, this is like crazy method where you compute this derivative instead of using all these approximations. This theta hat is the result of some many gradient descent steps optimization algorithm. You just like backpropagate through that entire thing and just compute this gradient. So there's like all sorts of tricks people do. Yeah. So how applicable this is to deep learning is like open, and there's a lot of work to be done in improving those. And okay, this is something a point which I want to make. So all of this approach of defining data valuations really assumes you have a value, you have this utility function, you have this function v, you can actually, you know. But in ML, we don't really know this v because this v is the population loss. Whereas what we have is only samples. At best, we have validation data, which is a finite number of samples from this. So just like in the stochasticity thing earlier, when we try to take this game theoretic approach and apply it to the ML problem, the fact that this is a statistical object has effects and is not really well considered. So it induces, so V is a statistical object, and it also induces dependencies between the, so now the data valuations are random, but also depend on each other because of this. How do you take this into consideration into all of this like clean theory we had earlier is unclear. And it was also like one of the questions I think Adam was trying to ask. How can we like extend that leave one out kind of framework to the Shapley framework is really unclear. And this actually has like real consequences. So suppose one of the main reasons you want to do this kind of data valuations is so that you can make decisions based on it, so that you can decide which data to buy, how much to compensate, or more generally which data to select, right? Like you're using these data valuations to actually select your training data. Now you have some number of validation data points, out of which you are computing all of these data valuations, and you're using these data valuations to decide between 2 to the n options. You're using n val data points to decide between 2 to the n number of options, where typically your validation data is much smaller than your training data pool. So n val is much smaller than n. Your statistician sense must be tingling here that this is fishy, right? Yes.
Yeah, but you don't need to find out the best subset, but I think at least you just want to be better than the original full training, right? I think that's certainly feasible. For instance, you just remove some of the bad data.
That's a good point. Yes. Yeah. So we should not really. The notion of optimality here is though to pick the best out of these.
Yeah, but in practice, you don't necessarily need to find, the optimal subset, right? You just want to, at least you just want to be better than the original using the full training data.
Sure. I'm not saying we're trying to aim for the optimal. I'm just saying that these are the number of options available to us. Mm-hmm. We don't a priori know which is the bad subset and which is the good subset, right? So we still have to decide between these 2 per n options. This decision might not correspond to a optimal decision, but we're still deciding between these many choices. And and you can actually you can actually do really badly. There are cases where you can do really bad. So, for example, let's throw away all computational constraints, and let's just pick the best subset of the training data which maximizes our validation loss. So suppose we do this, right? We just pick the subset S, So if theta hat S is the model we would get if we only trained on the S subset, and we pick the subset S such that the validation loss is minimized. So this is quote unquote the best subset, as our validation loss indicates. If you use this even for like very simple problems where your train validation are all IID, even then you can show that your error is at least, say, noise over number of validation data points. Whereas if you just didn't do anything and you just use the entire training data set, you would have gotten sigma square over n, where n is the full training data set. This is much, much smaller than this. So by doing all this additional work of selecting data, you could be hurting yourself in the foot. So I'm not saying that it doesn't work. What I'm saying is it doesn't always work. We know there are cases where it doesn't work. So when does it work? Like, what property of the real world data is allowing these things to work? Yes.
I'm essentially asking, like, when is this adaptive data analysis feasible? Like, because 2 to the n retraining, 2 to the n valuation calls, you need 2 to the n over 2 perhaps fresh validation.
So so ideally what you should do is, if you're doing this to whatever number of calls, you should use fresh validation data each time. But here we're reusing the data.
Times, maybe using
right. Yeah. So, but here we're reusing the data. Our validation data is fixed. So how should we account for the fact that we're using the same we're using this validation data to compute all of these different data valuations when making decisions? These valuations are not independent, basically. They are interdependent on each other. So when you take the max of them, you might run into these kind of issues. Yeah. Okay. And I think I'm nearly out of time. So of course, like, all of this I just completely abstracted away the distributed nature of all of these things. I just assume that was not even a concern so far, but for everyone in this workshop here, you ideally want this data set not be aggregated in a central way. You want these things to be implemented in a distributed manner. So how do you come up with distributed algorithms for all of this is an open question. And I think this is my almost last slide before the summary. So, and in the morning, we saw this entire mechanism design perspective on what is the effect of different schemes of different payment schemes or different different mechanisms on the contributors. Here we had none of that. The starting point was we don't really understand what is the effect of using data valuations as compensation. Basically, all of this kind of Shapley value theory is retrospective. You say, suppose n people came together with their data sets and pulled them together. How should you redistribute it? But the fact that you're computing these contribution measures and using that to make decisions will influence what people bring to the table in the first place. And that has not taken into account in any of this so far. So how do you connect all of this like very messy stuff to what we heard in the morning today, where we actually have to reason about people's incentives and actions, right? So how can we design these data valuation methods more from like a mechanism design perspective rather than just a fairness perspective or just the statistical leave and out kind of a perspective? And if you just use current data valuation methods, if you just use current data valuation methods as compensation, things can get arbitrarily bad. And I think this was Katrina's question earlier. What is the relationship between this data valuations and this proper scoring rules? Can we incentivize people to report real data? I think this has, so the proper scoring rules are quite stylized. They're like the theory there is, I think it's usually on discrete variables and like very, very clean IID settings. So can we take some of the ideas from there into this much more continuous, high-dimensional, heterogeneous spaces? If you think about it, this is essentially what we're asking is some kind of outlier detection. So what you want to do is, given n people, you want to see, is there an outlier? Is this DI really weird in light of what everyone else is saying? You want to detect this outlier and somehow penalize them, right? Like that's essentially what these proper scoring rules do. Yeah, can we bring that perspective into this data evaluations more generally? And yeah, I guess like more broadly, what are the different interactions between the game theoretic properties, the approximations, and so on? Okay, I'm going to skip this. Oh yeah, I'm going to skip this as well. So in summary, so just to summarize what we went through, we went through this like really nice theory about the Shapley values, which provide this unique axiomatic definitions of how to do data evaluation. But then we saw that this computation was just infeasible. And so we went down from this 2 to the n to maybe even like multiple constant number of training runs using these kind of very heuristic approximation methods. And they have like a bunch of applications. And really, the open questions are trying to connect these two together and trying to connect the gap between that, and the gap between these and the mechanism design we heard in the morning. So nothing in between is known right now, at the interplay of the statistics and game theory and computational concerns. Thank you.
I know there were some questions, and we're out of time, but I still have to allow one very quick question if there is a burning one. Okay, well, we have a break right now, so feel free to question Praneeth, and thank you, Praneeth, again. We'll meet in 30 minutes at 3:30 here, where we have the Richard Karp lecture by our very own Katrina. So see you guys in 30 minutes. Thanks.